In section 5.1, we talked about the normal distribution and using the 68, 95, 99.7 rule in the first half of 5.2. In this second half, what we're going to do is we're going to work a little bit more with what are called standard scores. So I'm going to go ahead and get this pen set up. So remember before, we could use that rule, the 68, 95, 99.7 rule, when we had something that was 1 deviation, 2 deviations, or 3 different deviations away from our mean. So if it was within 1 in each side, we had 68%. If it was within 2 standard deviations of the mean, we had 95. And if it was within 3, we had 99.7. Well, we need to have a different way to look at it. If it's not, so if we have a data value that is not exactly 1, 2, or 3 standard deviations away, right? So like, let's say that we have a data value that lies somewhere in here. Well, we know what to do if it was 1 standard deviation away, and we know what to do if it was 2, but we don't yet have a way to determine anything besides those exact distances away from the mean. We also need a way to compare data sets with different means and different standard deviations. So again, remember that the shape is determined by the mean and the standard deviation. So let's say, for example, we were talking about heights of females and heights of males. And again, this is just an example, so don't think that this is the actual representation of these data sets. But how would we be able to say, well, is a female with some specific height, would that be considered to be taller than a male? Right? So what percentile does this woman lie at? And what percentile does this man lie at, or man? And then we can say which is in the higher percentile or which is in the lower percentile. We know if we're just looking at the heights, right? We know if we're saying, oh, this woman is 5 feet and 5 inches, or this man is 6 feet, we can say, well, the man's taller. But in respect to all the data values in that data set, we need to be able to say, well, compared to all the other values, which one is on average taller? And that's going to be where a value called the standard score or also known as the z-score comes into play. So what we're wanting to do is we're wanting to take these two different distributions and we want to make it to where it's standardized. So now we're not looking at two graphs that have a different shape, but we're going to say, well, let's use some formula so that everything is on one distribution. So again, if we had this as our female heights and this is our male heights, we can say, well, now if we come up with a standard score, we can place the woman somewhere on this standard curve and then compare it possibly to that male height. So we're going to take both and standardize them onto one shape of a distribution. To do that, we want to calculate z as the data value minus the mean over the standard deviation. Let me go ahead and work through just an example here of getting a standard score, and then we'll work through what exactly that information is telling us. So let's say that we have an IQ test. And this example that I'm giving specifically is in your book. It is not one that I wrote out on the completed notes. So I'm just doing a separate example to talk through what the standard score is actually representing. So we have an IQ test where the mean is 100 and the standard deviation is 15. What we want to do is we want to look at this as far as a standard curve. So on our standard curve, we're going to assume that our mean is 0. And the standard deviation is going to look similar to how we saw it before, where here we have mean plus 1 standard deviation, mean plus 2, mean plus 3, minus 1, minus 2, minus 3. So it looks similar so far to that 68 rule. But notice that before, whenever we had a curve, we would say, okay, well, our curve is going to have this specific mean, and then each value out would be a standard deviation away. So this would be 115, 130, 145, and I'm going to just draw an arrow here saying the same on the other side. When we're standardizing it, we are not going to use the individual data set values to label our curve. Instead, we're labeling our curve with standard scores or z-scores. So let's go ahead and compute a z-score for this data set. Let's say that we have an IQ of 85. And I want to know, what is that z-score? So I'm going to take z equals our mean minus, or equals our, sorry about that, equals our data value minus our mean over the standard deviation. And we would see that z ends up giving us a value of -1. So just as before on our curve, I could see that this value of 85 would have been here. It's going to be the same on our standardized curves. We have the same location. It's just instead of marking it as our data values, we are going to mark it as far as its z-score. All right, let me go ahead and draw another curve. And I'm going to use the same mean and standard deviation information. So our mean is 100, our standard deviation was 15. I want to find a standard score or a z-score for an IQ of 125. So notice I have z is equal to the data value minus the mean over the standard deviation. And we end up getting a z-score of 1.67. Notice how I've been rounding all of these z-scores to 2 decimal places. In general, that's the rule we want to follow with z-scores. So always round it to 2 decimal places. If this is our standard curve, notice I'm labeling the z-scores down here. So this would be z is 0, z is 1, z is 2, 0, or z is 3, z is -1, -2, -3. And we can see that the z-score that we have for an IQ of 125, we can see that it's greater than this mean. So it would make sense that it's on the right side of our curve. And we can see that it's the case. 1.67, we would be about here. So what we want to do with the z-scores moving forward is we want to be able to find the percent of data that lies on our curve, either below that value, above that value, or between 2 z-scores. So what I'm going to do now is I'm going to clear the screen and I want to show a quick table. So let me go ahead and just get a curve out here so we can visualize what's happening. And these are all standard curves. Remember that the area under the curve is 100% or 1, depending on how we're denoting it. I just want to get a couple of curves out here. And they're all standard, so I'm going to label them accordingly. And I'm going to just put some hypothetical z-scores out here. Okay, so in this first one, let's look at a z-score of 1.67. So I'm just using that same one from our last example. We know that we would be about here. Before, we were able to say, okay, well, I know how much data is below that, right? If it was 1 or exactly 2, I would take this half of the graph, and then I would say, well, is it half of the 68, or is it going to be half of the 95? But I can't do that if it doesn't fall exactly on one of those values. So instead, I need to use a table to figure out how much of our data, or what percentage of our data, lies to the left. So I'm going to go ahead and switch screens just for a second. And I'm going to cool. All right, I'm going to go ahead and clear the drawings. And notice that I switched to page 370 in your textbook. We're going to use that table and also page 371. So these are our z-score tables. Notice at the top of the table, we have a curve, and we're given some positive z-score. So just like before, we had that positive 1.67. And we can see the area to the left is shaded on both of these, right? So whether it's a negative z-score or a positive z-score. What this table is representing, and I'm going to make this larger for you. What this table represents is the area of the curve to the left of that z-score. And you want to read this table just like you would a map grid or like Battleship, for example. So I'm going to go to this one. Notice in our example, we were using the z-score of 1.67. And let's say we want to know the percentage of data that lies below that. Well, what I would want to do is I would want to find the first 2 digits of our z-score. So notice here I have 1.6 as our first 2 digits. And then I want to find our last digit here of the 7. And I'm going to go down and across. Until I get a value that gives us 1.67. And this is telling us the probability or the percentage of data that is less than whatever data value lies at z equals 1.67. So I can see that 95.25% of the data lies to the left. I'm going to go ahead and go back to our note page and just get a couple more examples out here. Actually, I guess before I do that, I'll just use this table and just come up with a couple examples while we're at it. Let's say that I wanted the probability of having a value less than a data value that gives us a z-score of 0.23. Okay, so I know I'm positive. I know that if I were to sketch this, right in the middle would be 0. I'm going to be right to the right of 0. So this is going to be z is equal to 0.23. So just based off of the information that I know that half of my curve is 50%. So I shouldn't have a value that's too much more than 50% since I'm so close to that. So again, I'm going to go ahead and I'm going to say, let's go to the table. I want to find the first 2 digits. So my first 2 digits here are 0.2. So I'm here. And my last digit is 3. So I can see I have a value of 0.5910, or essentially I could say that 59.1% of our data lies to the left of z is equal to 0.23. Let me go ahead and clear this. I'm noticing that this video is going a little bit longer than I wanted it to go, so I don't feel quite comfortable adding in area to the right or area between in this video. So what I'm going to do is I'm going to just do a couple more examples of just talking about area to the left, and then we'll have another video pick up with the remaining two situations here. So let me go ahead and go back to notes, and I want to add a couple examples. So let's say that we want to look at, I'm getting my black writing here. There we go. Let's say that we have a data set and we're told that the mean is 100. The standard deviation is 15. So we're going to go back to this information. I want to find the percentage of scores less than 70. Okay, so I'm given a mean and a standard deviation. For me to find the percentage of scores that are less than a certain value, I first have to see, well, is this a value that I can use my 68, 95, 99.7 rule on? So let's convert it to a z-score. I'm going to take the data value minus the mean over the standard deviation. And I can see that I can use that 68, 95, 99.7 rule because it's exactly 2 standard deviations to the left. So since it's exactly 2, I can use this rule. We know we have the 47.5% here and the 50% here. And I'm looking for what is remaining because I want the percentage of scores that are less than that z-score of -2. If I add those two up, I'm going to have 97.5. And I'm going to take that away from 100 to see what is remaining. So we have a remainder of 2.5%. Let's remember for a second that that z-score is -2. I'm going to go ahead and clear this screen, and I want to pull open that table we were looking at before. Okay, so we're looking at this negative z-score. We had a value of -2. 0.00. Notice when we go to this table, now we have the area to the left of -2, giving us a value of 2.28%. And we could be asking ourselves, why is this different, right? Like, why before did I have 2.5 and now I have 2.28? This is something that's really important. So that 68, 95, 99.7 rule is more of an approximate. So we can say approximately 68% or approximately 95%. But if we're looking for the true percentage that is below that, we're going to have 2.28%. So it is very, very important to note whether or not the problem says you can approximate it or it needs to be exact. So keep that in mind. Okay, I'm going to go ahead and stop this one here just to kind of condense the time on the video. And then the next videos we'll talk about how to find area or how to find the percentage of a value greater than a given z-score and how to find percentage between two z-scores.